All right, now we're ready. Now we can start, right? Terrible jokes about. My little guy loves popsicles, and they have the popsicle jokes on them. And I swear there's something wrong at the factory because in the entire box there's only three jokes. I'm like, give me something new. But I read them out all the time to all the kids and pretend like they're hilarious. And everyone's like, "That's dumb, Dad." I'm like, yeah, it is. It's a popsicle joke. All right, so we're gonna finish up linked list, do our positional linked list. Hopefully you had fun not having lab today. And then we'll do our midterm review. On Thursday, the midterm will open, 2 o'clock. You don't have to come. I'm not going to sit and watch you take it unless you'd like me to. Sure, I'm going to be here because I didn't schedule this midterm for all of my classes on the same day because I'm dumb. So I'll be here anyway. Um, but it'll be due 3:11 by 2 p.m. So get it done sometime before the next class meeting. And apologize if that's bad if it's over break, but you can forget about it and do it before class next week or 2 weeks if you want, or whatever works out well. So we gotta finish up talking about positional linked lists. So we did the regular linked list and we looked at the really fast at insertions, right? Because they're in worst case, they never have to resize. Right? The downside with our array-based lists is the worst case performance was slow. On average, it was fine. We do our fancy math hand waving and we say, oh yeah, it's fast on average, which is true. But in actuality, we know it is occasionally slow. So if we need to get every little tiny millisecond of performance out of an application, and we know we're going to be adding and removing and expanding and shrinking and putting nodes in and out, we know that might not perform as well. So if we need to do better, we can. So we go open up linked lists here. So the next iteration of this is going to make our linked lists easier to use. Right, so the only things we gave here, right, our public interface, our API, this idea when we interact with the class abstractly, all they know about is our public functions. We've hidden all these little helper things around here. They don't know about it. They just know they can add to the front, they can add to the back, they can remove the front, they can remove the back, they can find something, they can get an item out, they can set it, get it. We know these ones are slow, so it's not good for these ones here. But what we can do to make this more friendly and easier to use is we can give the end user of our class a position. Now, this gets to be a little bit awkward, um, and the way the book does it is okay. And it goes a bunch of extra work here where we're like validating the node that we're looking at here, and we'll go through all that. It's not too terrible. The idea is I can say, here's your position that you're currently at in the list. And if you know what position you're at, you can add before that position or add after that position in constant time. Worst case. Because if you know where you are, I can stick you in between those two nodes. But I don't want to give you this node idea where you have to know what comes before you, what has to come after you. You don't need to know all of that here. So what we do is we add a position class, which is a wrapper around node. So the idea is we're giving you a simpler version here to interact with. So you don't need to know all the details of it here. And it gets to be a little bit messy here. My goodness. I usually steal his code here for this one because it's just easier. So give me 1 second. I'll go steal from last time here because this will be faster than opening up the textbook and stuff. These are linked lists. These are positional linked lists. Here we go. So we got node, circular position. Okay, so here we go. So this is our positional linked list here. Let me go steal all of this here. All right, so I'm going to drop this in a new class. I like the one file here. Sometimes I go back and forth here. I think it's a little easier to see one file here. So this is our positional doubly linked list here. All right. So the idea with this one here for our class of a positional circular doubly linked list, yeah, sure. It's circular, yeah. Is you have a position that we're going to expose to our end user. So we're going to give positions back from a lot of these functions when we do something so that whoever's using my class can hold on to it. Hey, you added something, here's the position it was added to. And then from there, they can track back and forth. If they want to hold 10 different positions, they can have 10 different positions. Okay, here was the middle third, here was the back 2/3, here was the middle point. As many as they want to hold, they can have here because we're going to publicly expose these positions for them to use. So the position references a container. So it says what container, what linked list do you belong to? That's why we have the reference here. So when we create a position, we say, okay, it belongs to this linked list. Because you can have more than one instance of linked list, right? You can have, here's my list of foods, here's my list of movies, here's my list of classes, whatever here, right? So positions will be distinct based on which container they come out of, what linked list they come out of. And then positions also hide the node. So positions know what node they reference here, but they don't give public access to that. What they'll give is the data stored at that node, right? Whatever that data that we were storing. So here, I just added a number 10. I added a number 20. I added a 30. That's the data here. So with a given position, you can get the data that it points out back out, right? Then the other thing we're going to do is we're going to look at, does it equal another position here? So I need to be able to compare, is this position the same as another position? Because occasionally we run into each other, right? So if I'm starting at the front and I have a back position and I want to go towards the middle, eventually my back position will equal the front position, right? Or as I'm stepping, right? So we're going to check, hey, are we positions here? Are we instances of the same class here? If we are, then we both have this node attribute. Then are our nodes the same? Do we reference the same node in memory here? So we can tell if they are. And then not equals is just not equals. Right? We don't have to do a lot of extra work here. We just flip it here. So we're not saying we're greater than, we're not saying we're less than. We just either we're the same position because we're pointing to the same node. However we got there, right? You started from the front and started walking. You started from the back, you started walking. Once you point to the same node, you're the same position here. So that we're equivalent here. And then node is the same here, right? It has data, it has next, it has previous here. We're singly linked. We have this dummy node that we set here. We have no items. Then what we add now is a way to validate position. So is this position a valid position? Right? Is it still active in my linked list here? So validate, okay, is it an instance of my position class first? Is it the right class? Is it the right type here? If it is, good. And then, is its container myself? Am I your container? Do you belong to me, right? Are you one of my positions? We're checking for that here. Then, does its next have a none? So one of the ways that we invalidate positions here, and this is just a detail of how we go about tracking that, we say if this position should no longer be valid, like if we want to delete a position, remove a position, we set its nodes next to none, which should never happen in a circular doubly linked list. You should always have something, even if it's the dummy node. So we know, hey, if your next is none, a bad thing has happened. This is no longer valid here. So we can't say it's valid. Then if all of that didn't raise an exception, we're going to give you back the node. So the idea here is when we interact with position, we need to get the node back out, but we want to go through all those hoops to make sure you're valid still before I get the node back out. Okay. And then we have a little helper make position that says, okay, hey, if we're the dummy node, give you none. I'm not giving you anything back because you can't point to the dummy node. That can't happen. Otherwise, make a position out of whatever node you're trying to make here. So this keeps us from going in an infinite loop here because eventually we'll get to none with the dummy node, right? So to add between two nodes, we did this one, right? This was our little helper function. We just go make a new node. We put its next is the next, its previous is the previous, and then we go, hey, the thing that comes after me, I come before you. Hey, thing that comes before me, I come after you. Right? We just put it into position. So this one's the same as we did last week, which we've all forgotten because Thursday was so many days ago. That's okay. And then new things that we're adding, right? What we're going to do is expose new functionality, add things to our public interface, add new public functions here. So if you want the first position here, I will make a position out of the first thing. It could be none, right? If I'm empty, you're getting back a none. There is no position available. If I've got something, right, because this make position returns a none if your node is the dummy node. If it's anything other than the dummy node, then now you have a valid position. Now you can, okay, here's the first position in your linked list here. Same with last. Right? The dummy node's previous is always the last thing here. Then we're exposing methods, functions here, that someone can get the next position or the previous position. So here, you wanted the first position. Great, here's your first position. Now, if you want to know what comes after that, you say, okay, hey, I want after, here's the position. We're going to go validate, make sure it's valid, and then make a position out of the next thing, which could be none. Right? If you only have one item here, the next thing is the dummy node, you get back none. If there's something next, you get back another position. So we're going to use that none all the time to say, okay, you've reached the end. There are no more positions left. They don't need to know that we're circular, right? That's an implementation detail we're hiding. We've encapsulated all those nice little details into our package because it makes our code nice and clean and easy. I don't have to worry about is my last none or is my first none and setting first and setting last and dealing with. I just have dummy node. Right? It's just easier for us to do here. And then we add more functions for adding before and after. If you have the position, I can add before or after it in constant time. No matter what, best case, worst case, average case, always constant. Because it's a linked list, there's no resizing that has to happen here. So if someone wants a list here, and this order matters, right? Because you have the first thing, you have the second thing, you have the third thing, but you want to be able to insert in between positions and not have to shift n items, this is extremely fast, right? On average, with an array-based list, to put something between two nodes, between two items, then you have to shift everything else, right? So on average, it was still n-based here. So with this one, adding before and after is constant all the time. This is a huge speed up. But again, you have to get to that position. So you can't just say, hey, at index 327, add something and a bunch of things shift. You have to go, okay, next, after 327 times. But eventually you'll get there and then you can add and remove in constant time. So there's the trade-off to getting to an index is a little bit slow, but then adding and removing, we're going to see in a second, is super fast. So again, depending on what problem we're solving, this is extremely efficient here. Okay. And then this idea of an iterator is really cool. We copy this out of the book here. The idea with an iterator is I can put this in a for loop. I can say for item in my positional doubly linked circular yada 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 class here, and I don't have to do anything extra. I can just use a Python for loop. That's what this iter is here. So the iterator lets us use that in a for loop. It's kind of some magical stuff in Python, which is really cool. You do these things in C++ and they're a little bit obnoxious. In Python, it's a little bit nicer here. But now I can put myself in a for loop, right? Really easy. We've not been able to do that in the other loops. You know, I had to say for range and index of length and go by index. So this is just more friendly. Again, you don't have to have it, but it gives you a nice friendly way of using it. And we add another special keyword here we've never seen before. It's yield. Yield is, again, a little bit of magic. So we're saying, okay, as long as I'm not none here, right, my current position, because first, if I'm empty, it's going to give me back a none because it's a dummy node. So if it's not the dummy node, I'm going to have something that's not none. I'll have a valid position that's not none. Yield says give this something. So it's essentially like a return, but it's a return and wait. So it says, okay, give this back and then remember where you are. Because you're in a for loop here, you have to hold on to that position until they ask for the next item. So in the for loop, you might have 50 lines of code. Okay, for item in my doubly linked list, positional circular doubly linked list, do something. And then inside of there, get that item out and do 50 things with it. Eventually, you come back to the top of the loop and it says, okay, give me the next thing. As soon as you ask for the next thing, as soon as the for loop says, okay, go to the next one, this code keeps on running. It says, okay, now you want the next one. What do I have to do? Okay, well, current goes to whatever comes after current. That's the next node. If it's not none, I'm going to yield something here. When this loop is done, I'm done iterating. And we have the same length. We have the same add last. We have the same add first. Delete, we're adding here. So if you give me a position, I can delete that position. Right? So I can remove from any given position here. All I need to do is take myself out of the loop. Right? So go to the thing that comes after me. Say, what comes before you is what comes before me. Go to the thing before me. Say, what comes after you is the thing that comes after me. Right? And then this node next is none. This is what we're doing in validate. We're checking for, hey, if your node's next is none, you're no longer a valid position. Because if you have a position that looks at a node that we've deleted, it doesn't work anymore. You can't keep that position. And eventually we return that piece of data. So you can delete a position, we'll return the data as the last chance you have to get the data out here. So we can give someone a position to work with here, and then they can add or remove behind it here. So this is really fun. So you can use it. Let's go back to main here. We'll go import it here. So from positional import, positional circular doubly linked. Oh my goodness. Okay, that might be a little too long, but that's probably okay. Okay, so we'll make one of these things here. So really all we need to know is that this is my positional list, right? So a positional list is one of these things here, right? Now with my positional list, I have an after, I have a last, I have a first, I have an add after, I have an add before, an add first, an add last, a before, and a delete. right? And the position class that it exposes here, I can use that as well. Now, the only way to add something though is to call add first, add last, right? So I have to add the first thing or I have to add the last thing here. So we'll do one of these. We'll add first. We'll add, what should we do? Like names, maybe? We'll add Eric here, right? Then I should be able to go get the first. So first then will equal my positional list dot first. Now I've got the first thing. This is the first position. Or maybe we'll call it current position, right? Current position is the first thing. Given this current position, then I can add before or after it. So if we want to add things in alphabetical order, I take my positional list and I want to say add after the current position. What do I want to add after? Well, the thing I want to add after is what data? Let's add a name. We'll add Jeb, right? Alphabetically comes after, right? Or maybe I want to say, hey, let's add before here. So take the current position and let's add Adam, right? If we want to do this alphabetically here. I still have my same position here, right? Still pointed at that same node, but now I've added something after, I've added something before, right? And if I want to get out the first thing, now first thing is going to be Adam, right? Because I added it before this one here. So I can change my current position if I want, go back to the first, or I could say, hey, my positional list dot before my current position, right? Go back one here. We got lots of different ways of interacting with this one, however we want to go about interacting with it, right? And I could say for name in my positional list, print the name, right? Because this will iterate over the actual data itself, right? With this little iterator, it's going to go give me back the data out of each position, starting at the beginning here. So if we give this a run, hopefully it doesn't crash on us here. We'll get back Adam, Eric, and Jeb, which is fun, right? And you can imagine adding more names and adding more names and adding more names and trying to keep them alphabetized, right? If we wanted to, we could go and find where this goes in alphabetical order by starting at the beginning and walking to next positions, right? Okay, get to the one after you. As soon as I get to one that is later alphabetically, I can add before it, right? So we could do that. So we can enter a name. We'll have name equals an input of enter a name, add to the list here, right? And then we'll take first. So my current position will equal positional list dot first. And then while my name is greater than the current position dot data, right? If I'm greater than means I come later in the alphabet, right? As long as I'm greater than, let's keep on going, right? So while name is greater than, probably while current position is not none, and the name is greater than that, right? Because eventually we might get to the end here. If we're none, then we're going to be done. We can't add anything after that, right? Um, then we can go, we'll take our current position equals my current position dot after, oops, sorry, the positional list dot after the current position. Right, go to the next one here. If name is greater, go to the next one. If name is greater, go to. How did that happen? That was freaky. They're not motion sensor, or there's a switch, right? Like that's a physical switch. The lights just turned off on us. That is crazy. Definitely not a short circuit in the wires in this building, I'm sure.
Well, across the way it has lights, so
Oh, wait, the projector's still on too,
yeah.
right? Like
Huh.
that's fun.
Alright.
Okay, yeah, why not? All right, so let's go. So we're going to keep on looping here. Eventually, this loop will stop, right, where I am no longer greater than, and I can put myself before that one. So we'll take our positional list. I want to add before my current position, and let's add the name, right? And then we'll go print out all the names. So let's see if this one works for us here. So what name should we add to the list?
Josh.
Josh. Oh, I probably don't need quote marks, do I? Oh, uh-oh. We validated a type error. Where did we get a type error? For add before. Uh,
I'm gonna validate.
line 37, validate. Oh, I think I got to none. Yeah, because Josh would be the end, would be the last one. So my loop is faulty here.
Offer list for this.
Eric,
It was Adam parenting.
Jeb with capital J.
Uh,
Yeah, so adding to the end, current position is none at the end of this loop, right? So we can say, if current position, right, added after, otherwise, else positional list dot add last, right? If you get to the end here, there it's none, so it's not going to work on it here. So I know it has to be the last one, right? So I think this will probably fix that. Let's give it a try. So we're going to add Josh. There we go, and now it adds to the end here, right? Last one alphabetically. So that's just my being sloppy with the code here. So eventually we'll go find where it belongs, or at the very end here. So if we wanted to, we could track multiple positions and just, hey, keep the end here and say, okay, hey, if you're greater than my end, don't start at the beginning. Right? We can save some time. So we can add in some additional code here, right? We can say, hey, last position is my positional list dot last here. And then just a quick check, right? If my name is greater than my last position dot data, then I can just go add last here, right? Otherwise, I can do this thing here. Oops, that one. Tab in, right? If it's not greater than the last, I know it's going to exist here, right? And really, I can skip this one here because I know that won't happen, right? I can save a little bit of code here, right? Eventually keep on going, and then when that's done, then we'll positional list add before the current position, right? Whenever that loop is done, we can stop, right? So we can be efficient. If I've got a really big list, right, we can keep a pointer here, we can keep a position here, we can keep a position here, we can keep a position here, as many as we want to do some quick checks, right? So I don't have to loop through 500 items. Maybe I keep a position every 50. But I can, okay, no, I'm going to skip 50, I'm going to skip 50, I'm going to skip 50. So even if the list, if we need to move around a lot, by holding more positions in memory, we can still have fast performance, right? And if we're smart about it, like hold, every time we double in size, we keep another pointer, right? We can essentially keep this from getting big, right? The way we did our average doubling, we amortize that average. So let's add Josh. That's the end here, right? So this one must run, right? And the else block didn't even run. And we can do that sort of thing. And we can loop all of this, right? Keep entering names until you want to stop, right? If we wanted. While name does not equal quit or something, right? Keep on doing this. Grab the first, grab the last, and check. And then enter another name at the end of all of that. Maybe add the list or quit. Right. So let's keep on adding. So we'll add Josh. What other names should we add? Like maybe something at the beginning. How about like a Ben? So that add before. Oh, I didn't add the name here. Didn't finish my ad before. That's my fault. See, if any code we write, we should test. This is good. Josh and Ben, and should we add another Eric for fun? What else? Any other ones? Carlos, Zed, A, whatever, and quit. And we should get out alphabetized if we did it right. Two Erics, Jeb, Josh, Zed. Seems like it's working, right? So we can hold on to those positions to get better performance. And that's the whole reason we're doing this, right? Some of the times it's faster, sometimes it's slower. It was really slow to get this particular index. We didn't even add that to this public interface. We didn't add a get and set item because we know that's terrible performance. If we know it's going to perform terribly, we don't have to write it. You don't have to give that as part of your API here, right? Don't let them do bad things with this tool, right? If here's my tool, like a stack and a queue, the only things you can do are push, pop, and beak with a stack, or NQ, DQ in front with a queue. We don't let them have the other access to things here. We're limiting what they can do because we know it's really fast at this. Right? We're making a very specialty tool for specialty problems. Right? For some reason, they have that star-shaped bit on the Ring camera, and I have to get my star-shaped tool that they gave me. I can't use a regular screwdriver to go unscrew it from the front of my house here. And I've lost that tool once and had to order it again because I'm stupid. and they want to charge like $5 for this little like plastic handle and a bit.
Yeah.
Like it costs them maybe 30 cents.
Like it's just like a normal start.
Instead, I should have just tried to get a normal star bit. I didn't think of that. I was like, I must have to get the ring one because it's special.
A specific one, but I just wanted you can get like not just like you can get it from like
Okay. I remember at one point they offered a one-time free replacement if someone unscrewed it from your house. They're like, okay, the first one will replace for free if someone comes and steals it, and they're probably going to be on camera stealing it anyway, right? Like,
right.
oh my goodness, that's a mess.
This process, can you now keep that next to once you quit? Does it go back to the three names you have in there?
So, yeah, I didn't save anything here, right? We'd have to save it and then go re-add it or recreate it in memory. And that would be slow to load something from disk and put it in memory, but that's always going to be no matter what kind of list you have, reading it in, right? Um, yeah, so we could write it out to a file and reload it there.
But that's the only way to update a list.
Yeah.
Update this.
Yep. Yeah. So we get really good performance if we want to put in the extra work of tracking our positions. So if we know our list is mutable and going to change a whole lot, like the regular Python list deals with that a little bit because they're oversized. So you can get somewhat faster performance for append, 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 but any inserts or any deletions are going to be n-based because you have to shift everything. So anytime we're dealing with lots of insertions and deletions, this might perform better. Again, we can actually measure how often we're inserting and deleting and how long it's going to take to get to positions, and it's a trade-off, right? We have to hold additional things in memory. Right, that idea of the space complexity. I'm using more memory to store this because for every item I now have a position and a node and a next and a previous, like there's additional things I have to store to track all of that here, but it's going to run faster, right? So if that's your goal is best runtime, sure, go for it. Memory is pretty cheap, right? That sort of thing. This one okay? So we'll play with positional lists in lab in 2 weeks because we don't meet next week for break. The week after that, we'll meet when nobody remembers anything. We'll just play with positional lists, do a silly thing kind of like this. We keep something in a sorted order or whatever we happen to do here as we go. Okay. All right. So let's flip over to the midterm review. So I posted last time's midterm in files here, right? Yeah, the practice midterm. Question number 1, a free point, right? Did I mention again? Someone did a study on this. If you agree ahead of time, you're more likely not to cheat. So, first question, right? And number 2, true or false? Oh, you can't even see. Oh my goodness, because of that. That's lovely. I don't know what bar happened here. Um, okay, forget that one then. Number 3, what 2 things must you be able to identify if a problem has the potential to be solvable with recursion?
Base case and like a recursion test.
Yeah, so the base case, I know when to stop. And a recursive case or a complex case, can you simplify a complex case to approach a base case? You might be able to. Again, it's not the everything tool, but it is pretty handy. Right? How do you print each item in the linked list? Like in English, what are the steps here? Not what the code looks like.
Like
Yeah, if we have an iterator, sure. But like, what is the iterator doing? What was the idea with this one,
you
right?
have to like go next each time.
Yeah,
Like the item.
and go next. Yep, print the item, go next. Print the item, go next until you either circle around or you hit the end, right? Until you reach the end. Yeah, so it's the idea of walking. Here it is, go to the next one. Here it is, go to the next one. Here it is, go to the next one. That's all this is looking for here, right? How does a linked list data structure for storing items in a stack give a worst case time performance of O of 1? Why is this so fast?
First, the very first item. Worst case is the very last one, right?
Well, so anytime we're using a stack, how do we get O of 1 performance with a linked list in a stack versus, worst case with an array-based list, we knew it was going to have to double. So it would be a worst case was n. Average was still constant, but how does this mean a worst case is constant here? What is special about linked lists?
Because it doesn't have to have a number. It doesn't have to like items to the list. It just has like a point next item.
Yeah, it never has to double. It always knows where the end is. You can just add to the end. Just add to the end, add to the end, add to the end, right? It's easy. Or I think with our very first version, if you just always add to the front, You just take the front, remove from the front, take to the front, remove from the front, all the time. You don't even need any of the double E stuff here with a linked list structure. Yep, it never has to double, so there's no n-based worst case here. Yep. Three main ways of interacting the public methods of a stack. What are the three functions we give?
Um, pop.
Yep, pop,
Is it push?
push. Yep,
And fire or peak.
peak. Yeah, top. Some people say, yeah. Usually it's peak. I don't particularly care what you call it, right? Push, pop, and peak. I like that they're all P's, which is fun. Yeah, or the top of the stack, right? Yep. In an ideal world, unit tests would be extensive enough to ensure that when they're run, every line of code of the class it's testing is ran. Is that true or false? True. That's our rainbows and unicorn land. I know it doesn't always get there. Ideally, we do because any code that's worth writing is worth testing. But we get paid and we only have so much time in the day, and at some point they're going to say enough is enough. It's close enough, right? So sure, some testing is better than no testing, right? It's that law of diminishing returns. You're going to spend a lot of time to chase that last 10% here. Are you really getting a whole lot out of it? Kind of depends what you left for your last 10% to test. Describe a problem that's easily solvable with recursion and why recursion is a good approach instead of an iterative approach. This one is not Fibonacci, by the way. That's terrible with recursion. And every time I get someone saying Fibonacci. Yep. And why is it good? So, like the file system is a really good one. Right? You don't know how many folders there are. They just go into the folder. If there's a folder, go into it. If there's a folder, go into it. Eventually, you'll hit where there's no longer a folder. Now I have my files, right? To get my list of files. That's a pretty natural one. Like the Towers of Hanoi that we did was like 5 lines of code versus 50. Is just so much easier with recursion here. It's a good approach, right? Maze solving is actually not a good example of this. Backtracking is terribly inefficient. It's easy, but it's terribly inefficient. Once your maze gets too big, it just crashes, right? Like a 30 by 30 maze, and Python just quits on you because you get that overflow. There's not enough room, the maximum recursion depth reached. You just can't go that far because it can't remember 900 steps, right? That sort of thing. So not good ones. But yeah, file system's really natural one. Towers one really natural. Things like that. Things with like a hierarchical structure. And it turns out we're going to use recursion with trees when we get there. We haven't got there yet.
I'm just wondering, like use factorials as an example too.
Which is not a good reason because you just need a loop, right? It's just you're adding overhead by using recursion because it has to remember every step of the way versus a loop just goes. It's a common example here, but not a good solution. How does using a linked list data structure for storing items in a queue give it a worst case time performance of O of 1? Worst case again. Same answer as the stack. There's no doubling. You never have to add. So this one we needed the doubly linked list because we needed to be able to add to the end but take from the front, right? And to add to the end, we needed to have the links both directions. So we could, or I think we could do it if we kept a back pointer, right? Is that what it was? I think we could.
Yeah.
Yeah. But then the deck, we needed the doubly links. That's what it was. But again, it never doubles. So worst case is always constant, never doubles. When creating a subclass from a class that has an init method with parameters, how do you call the parent class init method?
Super.
Yep, super parentheses dot init. Yep, just that keyword. Why does using a circular queue enable better memory usage? Probably. This was when we were doing array-based queues.
Because you can like reuse the same space,
Yeah.
right? It doesn't matter what position it's really at, just like as long as you keep track of what the front and the end are.
Yep. So it avoids never ending, right? The dumb one we looked at just never deletes. It just always expands. We said that was bad memory usage. So for circular, when you remove something, you can reuse its spot. Eventually, when you're full, you still have to double, but you can keep reusing spots as you add and remove. In your own words, why do we use a node class when creating a linked list? What does node do for us?
Positions.
Well, it stores the positions, right? It stores what is here, what's next, what's before. So we use it to store those things, right? Because that way you're storing the data and what comes before and what comes after, or just what comes before if we're doing like a single linked list here. Yeah, so it's that private detail here. Nobody needs to know about nodes. They just know, hey, they can add to my linked list here, right? So it hides all those details away of how we write a linked list. Because it'd be really annoying to have to do that by hand every time. Oh, I want to add before. We'll add it before this thing and after this thing. Like it just makes more work for people. So it simplifies how people use it, and we hide away those details. Um, what does the remove method do in English? Either linked list or array list. I don't specify which one.
So just replace it with not.
You don't want to replace it, right? Because then you've got a gap in your list. So if you remove an array-based list, we take it out and then we have to shift everything back in place. If you remove from a linked list, we have to remove that node and jump over it, right? Close the gap. Yep. Yeah, either one you want to describe is fine. Write a recursive. So this is the longer one here. Right? Write a recursive function that will accept a list and reverse the list without creating or returning a new list. Here, this used to be a really basic interview question just to throw at people to see what they did. And I swear, people with degrees in computer science would fail this, and it boggled my mind. Like, I don't even think that's performance anxiety. I think that's you just cheated your way through school and have no idea. Is my best guess, because this is like a 200 level question, right? Like we're doing that in this class here. So, pretty sure. Oh, we got to start up a new. Oh, I lost it here. No, PyCharm. There we go. We start up a new project. We'll do midterm review. This window.
Somewhere.
Yep. Let me pull that back up here. I think we did that in one of the labs, didn't we? Reverse a list, right? Now this is where you want a helper function because it makes your life a whole lot easier. A helper function, right? You want reverse to be easy to call, but I need a bunch of other details to do this thing recursively, right? So I want reverse some list here, right? And to do that, I want my helper reverse some list with a I don't know, front or start index and a back index. I don't know, current or last or something like that, right? So what's the base case? Well, when we've met each other or crossed over, right? I'm just going to start at the ends and swap, move in and swap, move in and swap, move in and swap, move in and swap. When I reach the middle, I'm done, or if I've crossed over, right? Depending if I have even or odd numbers here. So if my start index is greater than or equal to my back index, I'm going to return some list, right? Otherwise, if we didn't do that, we'll take some list. Um, here's the temp is my sum list at the start, and then we'll take sum list at the start and assign it the sum list at the back, and then sum list at the back will assign the temp. Technically, you can do this on one line in Python because it's super cool. It always confuses me. So if you ask the chatbot, they'll do a one line, and I'll know you asked the chatbot because nobody writes it in one line, right? But you can say some list of start, comma, some list of back equals, right? You can do it this way. Some list of back, some list of start. I've never seen anybody, oh no, that's start, right? Start index. Nobody writes that, right? I've never seen any of you guys write that code. But you can in Python, and Chatbot lets you do it. So I know Chatbot wrote it. That's all. Right? It's not meant to be a gotcha, just I'm telling you. Um, okay. So this is what normal people do. Hold on to it, replace the first, replace the last, right? And then we recurse, right? And then we're going to return.
You need to redefine what time is.
Nope. Uh, that's my, sure, sorry. That's going to keep going off this whole time. That's annoying. All right. Oh, shoot. Sugar's way too high. Sorry, that's my alarm. Let's try that. All right. Sorry. No, so every time we call this, temp will be replaced here.
Yeah, you need to have the thing having comma on the actual long time.
Oh, this one here?
Yeah.
Sorry, thank you. Yeah, I didn't delete enough of that. Thank you. Yep. didn't hit undo it far enough. And we'll reverse some list and then start index plus one, right? And back index minus one. So go further. So start at the ends, boom, 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 going on in. So all this outer, the public reverse does is call return reverse given some list 0 and the length of some list minus 1, right? You don't want the person to have to start by telling you 0 and length minus 1. That's just obnoxious. You could make this the only function, but it's not very friendly, right? And this is the ideal here. This is just much more friendly. Does that make sense? Right. And then the next question is, oh, I didn't have it in here. Usually the next question is do it iteratively. I missed that one. Sorry. Using big O notation, what is the average performance of something? Um, Average, most of these things is going to be O of 1, right? For inserting, I'm sorry, not inserting, for appending was O of 1 on average, right? Inserts were O of n because you had to do shifting. Removing was O of n, you had to do shifting. I guess it depends on which function we are looking at here. All right, here are the longer question ones. That's right, this must have been a quiz question. Um, that's probably in recursion here. Write a function sum of prime numbers or values in prime indexes given some 2D list. The return the sum of all prime number values and all prime values whose index is prime. Here. Be sure not to add the value twice. Oh goodness, right? And we just sort of count our prime indexes here as we go. Um, Silly, just a nonsense question to deal with 2D lists here, right? So we're going to have sum of prime values or values in prime indexes given some 2D list. Sure. Sum of prime values or prime indexes given some 2D list. Sure. Okay. So to know if something's prime or not, this one just go Google. You don't need to reinvent the wheel here and cite your source. That's fine, right? That's not the interesting piece of this question here. And at some points, I even gave you a prime. I didn't in this one here. Sometimes I'll just give you Python is prime. It's prime. There's a really clever function here where you stop at. No, this one's not even that clever. You can stop at the square root of the value here, plus one of whatever your largest number is for his prime. Yeah, this one here. You can stop at the square root for an is prime function, right? So starting at 2, going up to the square root here, and then usually you want to range by 2. You can check for 2, and then you can start at 3, ranging, but there's a bunch of clever ways you can do it here, which is fun. Number iterator, we don't want that one. I want trial revision. It's less than n. Goodness. One of these is faster here. This one. I think this is prime is probably the best one here. It's close enough, right? And we'll cite our source here. Right? We got it from here. Right, so we got to go import math. Import math. So we don't even need this one here. So if n equals 2, return true. Then we can start at 3 here. We want to range by 2. Ever so that way you don't check 4, 5. Don't check the evens. Because if it's not divisible by 2, then it's fine. Um, so so if we're not doing that one, right? Equals 2. Oh, we got to add one more check here. Sorry. So if n mod 2 equals 0, turn false. There we go. One last check here. So check for even. If it's not 2, then check for even here. Um, 1 false. Okay, and then we'll start at 3, going up to the square root plus 1, because you don't have any factors larger than your square root. Math stuff. Turn false, otherwise you return true. So sure. So we've got that. So first thing we want to do is loop through all the values, right? And counting index. So we'll say my current index then starts off. I think I said start counting at 1 because that's confusing here, but sure. I said, hey, this first one is, oh no, index. Oh, it does start at 0. Okay, so index is 0, right? And then we're going to keep on numbering the values we've gone through, right? 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. Just keep on numbering here. However many we have, we're going to go. So for row index in range, the length of some 2D list, right? That's the number of rows. And then for column index, and range the length of some 2D list at the row index, right? Because they're not guaranteed to be squares. If you assume it's a square, it's probably fine, but like this one was a rectangle, right? It was 3 by 4. As your first hint, it wasn't square. It's probably okay, right? We're going to check, is the value prime or the current index prime, right? So if my some 2D list at the row index, at the column index, and that's is prime, right? So is prime that value? Is prime, right? Or is prime the current index? And we need a sum then, right? So my sum or total probably is better as 0. We'll take the total, add to it that value. Regardless of if it was prime or not, right? We're going to take my current index plus 1. Okay? For every value I look at, go add 1 to the current index. And then add 1 to the current index, add 1 to the current index, add 1 to the current index, right? Keep on going. That's all this one is. And then when we're done, we can return total. So it should give me, if I added this right, uh, and this way we're not adding it twice, right? Should be included in the sum. 2, 3, 5, 7, 2, 5, and 7 are prime. And then these numbers are in prime indexes. They should be included in the sum. Did I not give a total? I thought I gave a total. 1, 2, 3, 4, 5, 6, 7, 8, 2, 5, 7, 9. Oh, man, that's a mess. That's fine. So let's try it out. So sum 2D list equals a list of lists here. 1, 2, 3, 4, 5, 6, 7, 8. And then what do I have here then? 2, 5, 7, 9. Right. 2, 5, 7, 9. And we're going to print the sum of prime numbers given some 2D list. Right. So it should be 1 is not prime, 2 is prime, 3 is prime, 4 is not. So we're at 5, 10, 17, 19, 24, 31 here. And then which ones of these were at prime indexes? This one was index 2, 3, so 4 more. Right, is that 35? 3, 4, 5. This one's going to get added to index 5. I lost count already. 41. 6, 7 is, so the 8 will get added. Oh my goodness. 49. 7, 8, 9, 10, 11 will get added. 60. Is that going to be 60? I got 58. Uh-oh. Is it right? Did we count wrong?
You're at 49, we added 9. We're close to 50. Oh, I was telling you to make your numbers.
I'm glad you guys can do math. My head hurts. I need more coffee. Did not get enough today. All right, so that's this one. Just using a 2D list for something. So you'll get a question about a 2D list here. Just navigating by indexes and doing silly things. If it's prime, just go look it up. Right? That's not the hard part of this one here. And feel free to use this one in the midterm review. Go for it. Right, a recursive function, a private helper function might be useful. Jumble recursive returns a new string where the character has been rearranged so that the last character is moved to after the first character, and the second to last character is moved to after the second character, and so on and so on and so on. So we're going to scramble it up here so that the last character gets placed after the first, the second to last gets placed after the second, the third to last gets placed after the third, until we hit the middle, right? So we're going to jumble. And then do it iteratively here. Okay, so jumble, define recursive jumble, given some string. Well, all this is going to do is call the helper function, right? My helper recursive jumble, right? Given some string, a start index, and an end index, right? Okay, then some string, right? We just call, we're going to return recursive jumble given some string starting at 0 and the length of some string minus 1, right? Same idea. Here's the endpoints. Now we'll keep on recursing here, but that way they don't have to call the endpoints. They don't have to hand it to you the first time. So to jumble this up then, some string is going to get really screwed up really quick here, right? Because we're going to be building new strings as we go here. And it's getting really messy, so it might even be nice here. This is like maybe the original string, and then maybe the jumbled string, original There we go. I like how it spell checks me. That's so handy here. So the jumbled string then is just nothing to start here, right? And I give it the start and end index. So what this one can do then is can take the first one and the last one, add them in. Take the second one and the second to last, add them in. Take the third one and the third to last, add them in, right? Until we meet in the middle somewhere, right? So that same idea. So if my start index is now, if it's the last character, like if they met, nothing has to happen, right? Because it's like an odd character. There's nothing to put after it here, so it stays. That should be fine. If they're oh no, I want to. If it's this just the one last character, I want to add it in. So if the start index is equal to the end index, right? I can return my jumbled string plus the original string at the start index, right? Either one is fine, right? Take that one plus that very last odd character, jam it onto the end here. Otherwise, then, right? Else if my start index is greater than the end index, we can return the jumbled string, right? If it's not either of those, so I have two base cases, right? Either we have one last character, I know how to solve that, or I'm done. I've passed each other, right? If we're even. Otherwise, we're going to take, we're going to return cursive string. The original string is the same. Then the jumbled string is going to be whatever the jumbled string was, plus the original string at the start index, plus the original string at the end index, right? Just take whatever you had here, add the first character, add the last character, right? Then take my start index plus one and my end index minus one. Work your way in, right? Why does it not like that? Too many arguments. Uh-oh. Did I have a comma somewhere? The original string, jumbled string plus start index, the end index. That's not an extra. What? I think this is just screwing up here. That's okay. Um, that should do it, right? So we should be able to try this then. So we're going to print the recursive jumble of A, B, C, D, E, F, G, H, right? Did I have H in there? No, just G, just a G, because that was an odd number, right? Uh, G, right? So first and last, right? We should get A and G, and then second and second to last, B and F, and then C and E, third and third to last, and then just the D, right? So we'd expect to get back out here. Let's see if we get that. Cancel, just run. I don't want to debug, just run. Oh, three positional arguments would take four, really? Cursive jumble? Oh, I called reverse. That's why it was yelling at me here. That's the wrong function there. That's what I get for type ahead. Uh-oh. ACB, and we stopped. None of that was right, right? Some string is the original string, given the original string, and then the jumbled string was nothing, start and end. So we should have taken, I don't know, let's see, let's put a breakpoint in, see what happens here. Right? Well, A, B, C, D, E, F, G, right? The original string, great. So the original string stays the same. The jumbled string is nothing to start. So the next time we call, let's step into our code here then. Now we're at A and C.
Started at 2.
How is end index at 2?
That's where it started.
The length of some 2D list. Oh my goodness. Wow. Some string. Here's what I get. I just kept taking suggestions with the type ahead and didn't even look. Hey, there we go. A, G, B, F, C, E, D. So it worked for odd. How about even? Right? So then that last one then should be A, H, B, G, C, F, D, E. Totally makes sense. We've jumbled up this string, right? Okay, so we did it recursively. Okay, now can we do it iteratively? Well, it's the same thing, it's just a loop now, right? That's actually easier to do without the recursion. This is like kind of a big mess here, doing it with recursion. So we can do just a jumble here. I'll take some string, right? And then the, I don't know, jumbled string, then equals nothing to start. And then we'll have a start index, a 0, end index is the length of some string, thank you, -1. And while start index is less than the end index here, let's jumble. Take my jumbled string, plus equals, right? Let's add to it the sum string at the start index plus sum string at the end index, right? Eventually it's no longer less than, right? So then I can just check, hey, if my start index is equal to the end index, then I have one last character to add, right? Return the jumbled string. Otherwise it's greater than, I had nothing left to do, right? One last check here. So let's try both, right? So
Increment the index.
I have to do that. You're right. Otherwise, I have an infinite loop. Thank you. Um, so start index plus one, end index minus one. Thank you. Yep. There we go. So now we can run that as jumble and recursive jumble. And the jumble, right, should be the same thing if we did it, right? We get out the same thing. Look at that. So once you've done it recursively, ideally the iterative one is much faster, right? Because you know what the loop is, right? So some question on writing something iteratively and then writing it recursively and then writing it iteratively. If you want to write the iterative one first, go for it. I'm not going to know which one you write first, right? Whichever one you want to approach is fine. And then the last one, write a class here. So again, the idea here is these probably take like 10 to 15 minutes per long answer question. So if you need a little more time, that's okay. We've got it here, but I'm not going to sit and watch you take a test. So our class burger with attributes for actual weight in grams, cost in cents per gram, a list for toppings, a base cost, and a base weight in grams. And then a method add toppings that accepts a string value, adds it to the toppings list, and a get total cost which returns the base cost plus the grams over the base weight in grams value, right? Cents and grams, cents cost in cents per gram. So like, hey, you get a 1 pound burger for one price for every gram above that, or kilogram, right? That's a big burger, like a half kilogram burger. That's even a big half pound. That's a lot, right? 250 milligram burger or 250 gram burger. Did you hear about the thing with A&W and McDonald's? McDonald's has the quarter pounder, and A&W said they wanted to be better, so they introduced a third pounder burger because it'd be bigger. And turns out when they surveyed people, people thought the third pound burger was smaller than the quarter pound burger, and they're like,
Smaller than four.
three is smaller than four because Americans are idiots. Why would I want a third pound when I can have a quarter pound?
Why don't I want a quarter? I can middle.
You see that? It's probably some stupid TikTok video or the reel. All right, everybody puts in $20. So you put in $20, I put in $20, and then I'm gonna buy $40 for $30, and now we both make $10 off of it. Like, no, the math doesn't add up here. It doesn't work like that. uh, people are dumb. People are sadly dumb. Which is sure. As much as we like to make fun of liberal arts education in college, like some additional education would be useful for people here. Okay. All right. So our class for burger. Class for burger here. If it's got some attributes, right, it's a init method, then either needs to accept them as arguments or set some defaults. Either way, it doesn't specify here, right? There's no specification what you want to do here. Either way is okay. So sure. So we'll just set some defaults, right? So a self dot here. Then we have a actual weight in grams. Self dot actual weight in grams. 0 to start. Self dot cents per gram. I don't know. 0 to start. Cents per gram. Cost in cents per gram. There we go. Cost in cents per gram here. Self dot toppings. Now that's an empty list to start. We have no toppings to start here. A base cost, so a base cost, 0 to start, and base weight in grams. There we go. Self dot base weight in grams is 0. Okay, great. These are public, so we can just go change them. That's okay, right? If we have an add toppings function, we have to go add a function for it, right? So maybe that indicates this should be private. They shouldn't go change it directly here. It's okay, right? Either I'm not particular about it here as long as we're adding it here. So we're going to define an add topping given a topping, self.toppings.append the topping. Right, go add it to the list here. Great. You want a burger with mayo and ketchup and pickles and lettuce and tomatoes? Go for it. Add all your toppings here. Right. And then we'll have a method get total cost here. So define get total cost, right? We're going to return my base cost plus, well, really, actually, we have two things that have to happen here, right? So my cost then will equal self.base cost. And then if my self.actual weight in grams is greater than the self.base weight in grams, right? If I weigh more, like you put enough toppings on here, right? Then I'm going to take my cost plus equals my self.actual weight minus the self.base weight, base weight in grams, times, and force some order of operations here so we don't screw this up here, right? My self.cost in cents per gram. I got to add my backslash here, don't I? That's fun. I'm zoomed in a little too far here, sorry. Right? Figure out what your overage was. How many grams did you go over? And you're going to pay that many cents per gram you went over, right, to that cost. And then we can return cost. If you didn't go over, you have the base cost. It doesn't matter what it is. So you do want to be careful to have this if check. You don't want to just calculate it because it could be negative, right? If the base weight is point or like 500 grams and you only have 250 grams, you're not getting a discount, right? You still have your base cost. That was the idea with this one here. Okay, set method for actual weight in grams, making sure that it's not less than 0 and no more than 1,000 grams. We don't make burgers more than 1,000 grams. Sure. Okay, so set for actual weight in grams. Define set actual weight in grams. That takes a weight in grams here. And if weight in grams is less than 0, I don't know, raise a value error or something, or weight in grams is more than 1,000, right? Otherwise, then self.weight in grams is the weight in grams, right? Make sure we have some sort of sane values here. Right? We put some bounds around it here. So probably if we've got a set method that should be private, I'm not too particular, but it'd be nice to have that sort of thing. So I'm going to go rename this one. Refactor rename. We'll say that one's private here. So you shouldn't go and change this one directly. Sure, that's fine. We've got a function for it. And then should be arguments provided to init and not have a set. I didn't read to the end of my own question. My bad. Okay. So cost in cents per gram, base cost, base weight. Not have set functions. Okay, sure. So we make this one's private. So cost in cents per gram, base cost, and base weight here. Then should be arguments. Base cost is the base cost. Here, the base weight in grams. We should just copy these things here, right? Equals the base weight in grams. And the cost in cents per gram. Sure. Cost in cents per gram. Okay. So we accept them as arguments. Great. Don't have set functions for them. Probably should add in gets. I didn't ask for gets. It's really boring to make you write get functions, and I just have the chatbot do them anyway. So I don't care about gets. Right. Then write unit tests to ensure 100% code coverage. So write a class and then test it. Right. Two pieces here. So 100% code coverage means if I've got an if block, it's running. Oops, that's right. I changed these things to be private here. I should have done the refactor rename so I don't have to do all this. My bad. There we go. So 100% code coverage means this if block has to run. I only need one test for that, right? A test where you go over the weight. If you're under the weight, this code still runs here, right? Now, it might make sense to test them both just in case, because if you screwed this up here and didn't add that, you might be subtracting money, but you still get 100% code coverage. So you can see testing's not perfect, right? That's okay. And then set weight, well, we need a set where we raise an error and a set where we actually do set it. So that means we're going to have two tests for that, right? Add toppings, sure, we can add topping. It doesn't actually do anything here. That's fine. So we want to add a test. So let's go to test. Create a new test. I want to test set and get here. So we need to from main import burger here. So we're going to arrange. We're going to act. Now we're going to assert. Is there only? Okay. So we know a expected total cost equals, I don't know, what do we say? If the base cost is $1 and then it's 1 cent per gram, we can say this is 105 or 1.05, right? And then we need a burger. equal to burger. And then we need a couple things, right? What was it? The base cost then will be $1. The base weight in grams we'll say is 100 grams, and the cost per cents in gram is 1 cent per gram to that, right? Sure. Think I screwed up in here. We're going to find out when I fail this test in a second here, because I'm charging dollars instead of cents, because I didn't divide by 100. But we'll watch the test fail, and then we'll catch it, right? Which is why we write our tests. Okay, there's my burger, and then my burger dot set actual weight in grams we wanted to say is 105, so we're 5 grams over, so it should be 5 more cents, right? And then we'll get the actual cost, then is my burger dot get total cost, and then we're going to assert self dot assert equal my expected cost and my actual cost, right? And when I run this test, it's going to fail. I'm going to be sad about myself here. It failed. 6 does not equal 105. Oh, I added $5 per gram or $1 per gram. Well, that's not good, right? So when I go add this here, that should be divided by 100, right? Because that's cost in cents here, right? Not dollars. Now my test should pass when I run my test here. Hey, now my test passes. Life is good. So that one's good, right? And then my test actual weight in grams here, right? We've got the self.assert raises here with a value error. And then what do we have to give it? The name of the function, right? Isn't it? So we need a burger equals a burger, and we don't care about any of these values, right? 1111, sure. Burger dot set weight in actual grams. We give it the function, and then we give it something like 10,000 here, and it should raise an error. I think that does it here. If you don't remember that, you can just use a try block and catch and do your search in the catch or something. Either way is fine here. For some reason, I remember that one. But this is raises exception, right? So we've got some code coverage, but it's not done yet, right? Because it didn't actually work here, right? So this one is set weight in grams, I don't know, works or something here. So we'll have a expected weight in grams. I don't know, 500. Let's make a big burger here. We'll make a burger, right? And then we don't need to raise an exception. And then when we're testing, right, we're testing our code. So burger dot set weight in grams to the expected weight in grams, and the actual weight in grams is my burger dot get weight. And we didn't write a function for that. Shoot. Well, if you want to test it, we should go write a function. Now I'm feeling bad here. All right, fine. Get weight in grams. I don't have to write that. Self turn self dot weight actual weight in grams. There we go. Okay. I get weight in grams and self dot assert equals the expected and the actual. Now let's give that test a run. Run tests. And that one passes, right? We're good. So when we look at our class here, all of our code, we never ran add toppings, but it doesn't actually do anything. So sure, one of these ones, maybe we'll add some toppings. We're going to add toppings. Nothing. Sure. I wouldn't care. Technically, we weren't at 100% code coverage because we didn't ever try that one. So now I feel a little bit better. We never tested if it worked because we didn't ask for a function to like get a topping list, but maybe that sort of thing might be nice, right? Like add a string function that overrides the string return and it gives you the list of toppings. That might be something we could do, right? That was it. What do you think? Not too bad. So literally question for question, topic for topic. So 2D lists, recursive and iterative, and then class and test for the questions here. So it'll start Thursday. We'll be until the following Tuesday after break. Lots of time. If it doesn't make sense, please ask me because I wrote the questions and you're familiar with me not making sense. So if it seems a little weird, just ask. Right? Reach out anytime. Happy to help whenever. We should be good to go. Awesome. Thanks, folks. I will catch you in 2 weeks then, right? Awesome. Have a good break.